And, you know, to Tony's point earlier, we are the only company bringing these different technologies together, and we're so excited to be able to highlight all these capabilities around ideation. But a very important element of what we do at Siemens, what we do in Siemens PLM, is this area of realization and how we bring products to life through manufacturing processes and new technologies to support them. So we're going to move into the second piece of the presentation around realization. And I'd like to welcome to the stage Tobias Long and Mike Roman and Aaron Nadal to help us with this. Meanwhile, Alan, I understand we have one of your components over here.
A little realization.
And I think the audience would love to understand what that is. So let's go undrape that, and I'll hand it over to Mike for the presentation piece. So I guess we should probably be careful with this as we do it, just because we've got some things underneath. But what we have is, I don't know. Alan, what is this thing?
So this is the nose section of the airplane, which houses the front landing gear. And so an aluminum structure, a bunch of machined parts, some riveted fasteners, sensors, control systems, the front part of the airplane.
Fantastic. Well, thank you, Jim. Thank you, Alan. Yeah, this is really great. And
it would have been better if we could have the whole airplane.
Yeah,
here, it didn't fit in.
We wanted you to bring your plane, drive it right in here, but we couldn't get clearance from the fire department.
That's an interesting point. Those of you that attended in Orlando last year might remember the fuselage without the wings on display. And as it turns out, we were in discussion to bring that in for this presentation, but there was no way to get it up from the basement to the second floor and get it on stage here, so we had to go with the front nose.
Right. So. Fly it in through the roof.
Oh, good. Well, this next set of demonstrations is about realizing the digital twin and improving production with that digital twin. And it's also about smart factories. So at Siemens, we believe that smart factories can transform business. And we believe that by giving companies next generation technologies, they can do incredible things in manufacturing to realize their innovative product ideas. And a smart factory is a digitalized, fully digitalized model of a production system, a digital twin for production. And it's connected automatically and fully to a PLM data repository via sensors and data collection systems and PLC controls and other automated devices. And the breakthrough strengths of a smart factory are additive manufacturing and advanced robotics, flexible automation systems, and virtual and augmented reality. And Siemens is delivering tools to companies to be able to create those digital twins and smart factories and allow them to achieve these tremendous innovations in their products. And the key enablers of the smart factory are the things that we would like to highlight today. And we have the good fortune of having the nose of the aircraft here to help us do that. So let's start with additive manufacturing. Siemens believes that additive manufacturing reshapes everything. And it allows for the reimagination of not only existing products, but the creation of entirely new products that we never could build before. And in this case, we're focusing on the nose of the aircraft. And there's a very important piece that goes on the front of the plane. It's called the radome. And the radome has a very important function. It obviously is instrumental to the aerodynamics of the plane, but it also protects avionics and antenna systems that allow for the very important transmission and reception of communications and other things that we need to be able to do. Like, for instance, today, folks want to watch streaming video on the airplane. That requires a certain level of frequency reception on the plane, and that demand for higher frequency demands a new design of the radome. And those radomes are typically built with composites and different kinds of techniques that oftentimes are difficult to build. And we believe that additive manufacturing can help you retool manufacturing to allow you to produce that type of design. And so with that, we'd like to focus on how we can zero in on that radome and take advantage of the capability with composites and different types of structures to reimagine the design, to produce a lattice honeycomb that will allow for scarcity, if you will, in the middle of the radome that allows for more frequency reception to increase the bandwidth that we can receive. And we take that lattice pattern, we wrap it around that inner dome that's based on the original design, and we apply some thickness, and we then put an outer skin on that, and we're able to, in our NX environment, reimagine the design of this radome. So that's pretty cool. But it also has to perform. And so we're able to then take this radome design, this reimagined design, and very seamlessly move it into SimCenter, apply the material conditions that are required for this particular design with the material that we're going to use from the material library. And in this case, we're going to do a simple simulation. I say simple, it's really not simple, it's very complicated, but we're able to make it look simple, and what we're doing is we're analyzing what might happen to this new radome design in a low impact situation, and we're looking for damage based on separation of the layers. Remember that this is a sandwich design. The inner dome, the outer dome, the inner core, allowing for the function of this nose. But what happens if this particular design with this material was to get impacted in a certain way? We would see, highlighted here by the red, that we probably would have an issue where we would see separation in those layers. Now we have the opportunity to go back and reevaluate this design, re-engineer it a little bit, maybe use some of the other tools that we have to ensure that this design is robust, that it performs. But that great design is only good if we can make it. And additive manufacturing allows us to make this radome in a much different way than we would typically make it today. The conventional approach for building this is probably a very complicated manual layup process with composites. We might have to purchase flat sheets of lattice that we then have to wrap and cut and work with. And those costs and time restraints can be problematic. Here, we have a completely different way of programming this to be produced on a multi-axis fused deposition modeling 3D printing system. This is developed by Stratasys in partnership with Siemens, where we use a robot to deposit material to print this shape. And you can see that it's being produced with little to no structure to support it, and on a very large scale. And this radome that we're printing, if it was full size, would probably fit on that airplane nose because it was designed for this aircraft. And so what you're seeing here is our ability to program it, to simulate it, and to see what the result would be. And oh, by the way, we actually made one. And so this robotic composite 3D demonstrator, RC3D, as Stratasys likes to call it, actually printed this part. And we have it here. So this is the part that's being printed. And I'll stand over here so you can see it a little bit better. So this is a cutaway view of that part. It's obviously half scale. It's not a full-size radome, of course. But we printed the inner layer. We then printed the lattice structure. We then put the outer skin on. And this was done on the system. And we have another model here where we have the completed part. Now, this is not a production version of a half-scale radome that would go on the Eclipse. Probably wouldn't function the way we want. But the point is that this type of technology is available today. The ability for us to reimagine this radome, to make sure that it performs and does what it's supposed to do, and then produce it, is something we can do today. We don't have to wait for the technology. We can start this process now. And if we think there's some value here, then we can derive that value. And the point is that the value here, and the point that we want to make, is that additive manufacturing allows us not only to reimagine the design, it allows us to change and retool our manufacturing process and rethink the business model that allows us to more effectively make and deliver this part wherever it needs to be made and delivered.
Okay,
And I think that probably
Mike, I
goes...
might just interrupt here. I just want to ask Alan a quick question on that. Alan's got an extensive background in composites, and I just was interested in your thoughts on what you see there.
Composites, meaning fiberglass, carbon fiber, and things like that, have been a long time coming to aviation. My first company, the first airplane, Cirrus, was a composite airplane. The Eclipse is primarily aluminum. But yeah, it is part of the wave of the future, you know, using the right materials the right way in the right places. This is just so cool. I can't tell you how much I love this. Because eventually it will be in structural materials, in primary structure. But to start with, the primary structure is the minority of the number of parts, and there are so many parts that need so many changes. And when you think about product differentiation, product improvement, and in the end, customer value, you always have to be looking at what's the next thing we can change, what's the next thing we can do, where the barrier is tooling cost, certification cost, design cost, and this is all the shortcut to that. So yeah, while you're doing this, I'm thinking of half a dozen different places where we would do this on the airplane.
Fantastic, very good.
Very cool stuff.
Thank you, thank you. Okay, very good. So continuing on, I'd like to invite Tobias up to talk to you a little bit about automated production and what we're doing in the area of production systems engineering to further develop the digital twin and the smart factory, and then we'll come back for our final piece. Tobias?
All right, thank you. All right, so traditionally, if we talk about building a factory and automating a factory, you actually work in different disciplines, and you work basically in silos. You push your results over to the other team, and you hope for the best. And if you actually want to see what is happening and how your factory really behaves, you wait for the equipment to be installed, and then you will get surprises, because nothing really works the way that you intentioned it if you can't test it before. So our way of thinking about this is that we actually offer a tight integration of our tools, and we weave a digital thread between the different disciplines and the data in order to allow a real digital twin that will facilitate already digitally verifying your factory way before it's being built. So we talked about the aircraft. We're going to talk about the inspection of the wings. So maybe you have an inspection station that is only working for metal structures that are being built, but you want to extend that. You want to use ultrasonic non-destructive testing, and you actually say, okay, we're going to include automation into that. Now we're in automation in Line Designer, and we're actually placing 3D robots on these and conveyor belts on this in this 3D environment. And as you can see, we just take them from the library and automatically place them on the floor. Now, we have 3D modeling capabilities in here, but actually we added a lot of snapping to the ground and automatically knowing where things belong on a factory. So we actually allow a lot of automation of that engineering process already here. So you'll see the same thing now with placement of the robot. Actually, we know where the robot belongs on that conveyor belt, so it just snaps into place. And obviously, if you need 3D modeling, you can always do that. We can analyze the reach of the robot, and we can actually show the product that is being inspected. So you actually have product and production in one environment. You can also do analysis, like, for example, you want to know which manufacturers are producing certain parts of your cell. You can go there and get that. But that's not all. So actually, while you're engineering, you can already send off your data and let others continue with the automation engineering, not the mechanical engineering. And you can continue do your engineering while the others are also working. So you actually just finish your engineering, send it off with a change notification to the other team, and then you say, okay, for this conveyor belt, also please add automation to it. we're going to continue actually to show how easy it is to add conveyors to this factory. So we talked about composites, and you actually want to bring the composites in from a different area of the factory, and actually these conveyors now automate that, and as you can see, that's done really quickly. And in the end, obviously, for commissioning, you need the full-blown diagrams to install the equipment. So now we are in Automation Designer, and we're actually going to use the mechatronical templates that we have to fuse the mechanical design and the automation design. We're actually just bringing in the standard equipment that you need for automating the cell, and you actually have code that is automating that whole process. But as you can see, there's red areas in this code. These red areas are actually things where you need to call other software blocks that control the equipment that is being placed in the factory. Now, traditionally, what you would do is you get a PDF with a layout plan of your factory. You get a spreadsheet from Excel where you actually have some data about those robots and conveyors, and you would actually get a third PDF that tells you about your automation standard. You copy and paste from 3 different systems, then you do some modifications, and hope for the best. Now here, you actually just select something in 3D, you place it over in the right structure, and tell it to be placed there. The code is automatically generated with the right parameters, and it just works. And it's 4 clicks instead of the 4 systems that you have to touch. Now, you've been concurrently engineering while the other engineer did the mechanical engineering and just came in the change notification. So now we bring in the 3D model of that conveyor, just with a click, and then we also automate this, coming from the library, all the automation components, and actually also the electrical schematics of this are coming with it. Everything is in the system, and everything is also being validated. So we have checks in the background that can tell you, okay, is it properly dynamized? You actually get the full-blown structure. You get the ECAD schematics, as mentioned, but you get the full-blown structure for the automation systems. And you will also get the ECAD pages that you actually want to produce for later wiring of that factory. Now we move over to actually simulation. So we want to see what the cell actually does, right? Now we bring in the wing. We transport it in. The conveyor belt behaves exactly as it's supposed to be. There's actually these little walls that go down because of the water for the ultrasonic inspection. And you select the signaling that the automation system normally would provide in this little table. And the robots, as you can see, they synchronize. They move actually around obstacles and then resynchronize. And you can do that for discrete checks. So, for example, you want to check one point, or you can do it for continuous checking of linear movement. So all of that is integrated into the system. Now, don't get me wrong, simulation is a great thing. You can check a lot of things already ahead of time. You can check the coverage. You can see if every part of the wing is actually being tested. You can do, for example, if you would analyze paint, you could analyze where the paint would go, all these kind of things. Simulation is a great tool. And a lot of other people would call this already, this is a true digital twin. Well, we as Siemens, actually, as Tony mentioned earlier, have a better offer because we have the automation systems also in place. So on the left-hand side, you can see the code that has automatically been engineered before that is being generated, and you can just use that code to virtually drive already your factory. So you're not only doing a simulation, but you're doing real virtual commissioning, which actually allows us to find any sort of mistakes you also did in the automation code, and you can basically debug a factory while it's there. So as a computer scientist, I always have to say, debugging code is great, but debugging a factory virtually is pretty awesome. So with that, we're actually offering a really integrated solution that brings together these different disciplines and actually allows for really efficient engineering. And through that, you can actually optimize your production facility much more easily during the process and facilitate the digital twin so you can create the factory of the future. Thank you, Mike.
Thank you, Tobias. Okay, now the last piece in the puzzle here is what we're referring to as augmented reality. I'm sure everybody's familiar with the term augmented reality. And the point here really is to change your viewpoint and change your perspective on how things can be done. And I'm going to, in a moment, ask for help from my colleague Iran over here to demonstrate this for you. But conventionally, we would see, I think even today, the process of getting from planning to production, a disconnected process. People working and throwing information over the wall, as cliche as that is, I think is still largely the case. And what happens is that we get out of sync, not everybody sees what's really going on, and that increases the opportunity for failure and for risk when we go to production. And those errors can end up in the instructions that get provided to folks who are doing assembly for us. And the interesting thing here is that the Eclipse aircraft is going to receive a new supplemental vision system, an infrared camera that's going to help the pilot, give them situational awareness when they're landing in low light conditions or bad weather, low visibility, avoid animals on the runway, these kinds of things. And that system needs to be installed on aircraft that are already operating today. So this is a retrofit type of situation. I'm going to do it in the field. I may also be doing it on production aircraft where I need to set up the installation of this in an actual factory where I have planes that are waiting to be worked on. And we have this idea that we can take advantage of technology like augmented reality to simplify the process of adding that item to the aircraft and making it easier for the operator to do that job, whether they're in the field or whether they are in the factory. So we're now going to switch to a live demonstration where we're actually going to use this nose because that would be a shame if we didn't. And what we have is that Iran is now reviewing the electronic work instructions that were provided to him to visualize what the task is, how to install, in this case, the bracket, the longeron, I believe is what it's called, that holds this system. The original one needs to be removed and this needs to be installed. So he's able to review the instructions, he's able to manipulate the 3D. He can also use now that electronic work instruction to guide him with an augmented reality view. So now he's seeing the virtual part overlaid onto the real nose. So he knows exactly where it's supposed to go. And this is interesting and important because this gets installed from the inside. So this is like an X-ray view for him, seeing from the inside where the part needs to go. He now takes the part and he's actually scanning the part. That part has an identification on it. Do I have the right part? Is it associated to this aircraft? Yes. He gets the green check mark. You have the right part. And now he can go to the installation process. So he's now going to utilize the augmented reality system to help him position the part. He installs the part, and then he asks the system to validate for him if the installation was done correctly. And in this case, you know, you didn't do it so right, okay, something's wrong, okay. So the system understands where this part's supposed to go, how it's supposed to get assembled. He now repositions the part, and then he'll ask again for validation. The system will check, did the part get installed in the right place? And hopefully, if he did it right, yes, in fact, he did. And so we have the ability to guide the operation to ensure that we've got the right parts, that we've installed them correctly, and that it's passed the installation test, if you will, if I can say it that way, to make sure that we did it correctly. And that could potentially lead to conformity that we need to have, and ultimately, not certifying necessarily, but making sure that from an internal point of view, that particular thing was installed correctly and that the job got done. So Ron, thank you very much for your help.
Perhaps just interrupt you here for a second, Mike,
yeah,
and ask Alan. You know, from a certification perspective, how is augmented reality applied, or is it allowed by the FAA and the record keeping and those kinds of things that go along with that, and working through the engineering work instructions according to augmented reality. What do you see there?
So it's already used in aircraft production from an FAA point of view in terms of how you use lasers for placements, particularly in composites, things like that. But clearly what your demonstration does is touch upon all of the things that are necessary, which was first, how do you design the part, how do you certify the part, then how do you install it, again looking towards this concept of conformity. How do you document that the work instructions were followed, that the part was installed in the right part was installed in the right place on the right airplane, because some customers won't want this feature. So yes, all of this leads towards that integration and simplification, which should in the long run improve aviation.
Okay, so again, the point here, augment your reality, change your perception and your point of view to how things can get done, and take advantage of technology to help you produce those innovative products, install them correctly, deliver them when and where they're needed, and most importantly, make sure that the job is done correctly the first time, without error, and that it's immediately validated once it's done. And with that, Jim, I believe I'll be turning it back over to you.
Yeah, good, very good. Mike, team, thank you so much. Excellent.